So continuing on, we're going to get into the second and third laws of thermodynamics today. We did the first law last time, and today we're going to talk about entropy. So, crazy entropy. Everybody likes to talk about it. There's some great cartoons out there. And then related to entropy is heat capacity. So we're going to really dig into that too. So again, this heat capacity per mole, your notes have a little less significant figures on there for water, but for water, it's really 75.38. I have like a roughly 75 on there. What's that?
I don't think we have these notes.
No, really?
It's a different one.
Let's see. Oh, yeah, okay. Yeah, well, it's still there. It's just missing this slide. Okay. Yeah. So I just did this one mainly for vocabulary. The difference between heat capacity and specific heat. And so when we talk about heat capacity, we're kind of giving you a hint in terms of the units, right? Heat capacity is per mole, and specific heat. Whenever you see the word specific, okay, we're talking about mass. All right. So it's joules per degree Kelvin per gram. Okay, but that's the same as the other one. If you just multiply this by 18, grams per mole for water, then you get the 75. Okay, so they're related to each other. They're both heat capacity, but one is per gram or per mass of substance. The other is per mole of substance. Heat capacity is per mole, and the specific heat is per gram. And then you're going to be, just like me, confused when people say specific heat capacity, because that has all three words in there and you have no idea what they're talking about. So you have to specify there, like, wait a minute, are you talking about per mole or per gram? So that's a common confusion. Okay, now in the, there's another unit for heat capacity down here, in energy, essentially, energy. And that's calories. You guys have heard of calories. Well, the specific heat for water, and I guess the original units that we talked about in terms of calories, okay, was 1 calorie per degree. And it was originally degree C per gram. And so water not only defined our temperature scale of Celsius from freezing to boiling, so 100 degrees in between. It also defined our energy scale here, in that it took 1 calorie to heat 1 gram of water, 1 degree. Okay, and so then converting this over to that, we get the definition or the conversion factor of joules. There's 4.184 joules per calorie. So that's the conversion factor for joules to calories. And then you have kcals, obviously, is 1,000 calories, but that's also a nutritional calories with a capital C. Now we're getting crazy because we're getting into case-sensitive units, which is the first example in our course of a case-sensitive unit. If it's a capital CAL, like on the back of a nutritional thing, it's really kilocalories with the lowercase c. So it's 1,000 calories. Yeah. So that's just, I'm sorry, I didn't do this to you guys, but so CAL, oh, I can't. Okay. So capital CAL is 1,000 little CALs. Definitely not the metric system. We started getting away from this kind of craziness and putting prefixes in front of it, kilo, mega, giga, and all that. So I like the metric system way better. Okay. So then whenever we determine the internal energy from a change in temperature, we're using this heat capacity at constant volume. We've already done a few of those calculations. And we assume that the CV is constant over a range of delta T. We're going to look at that some today. Okay. And then since work is 0 with constant volume, we're not expanding or contracting, then the change in temperature with heat input can be used to determine CV. So we can take, this basics of our calorimetry experiment. We can measure the delta T, and if we know the heat capacity, we can determine the heat. If we have a reaction that gives us a known amount of heat, and we measure the change in temperature, we could solve for CV. And so we do that kind of calculation a lot. So here's a review of the equations we've covered so far. So these were kind of the last few slides in the last set of notes. And so I brought them forward because of the sort of the glitch and also to emphasize them. So we've calculated work twice or two different ways. And so you want to make sure that you know the situation that is related to each of these. So calculating work for a particular process, you need to look at it and say, am I pushing against a constant pressure? So this right here is a constant pressure. So that would be said in the sentence, right? Like or in the word problem, you know, a piston or a balloon expands against a constant pressure of 3 atmospheres or something like that. Then you know that P external is 3 atmospheres. And you take the delta V and you can calculate the work that's done. Okay. For the isothermal, you've got to see something like this word right here, isothermal expansion. An isothermal expansion is probably assumed to be reversible, so the reversible word may or may not be there, but these are the clues that you see because you've got 2 equations to calculate the work. Which ones do you use, right? So you've got to really look at the context of the situation. If it's isothermal reversible expansion, notice pressure's nowhere in here. Okay, that's another clue, right? You can't do this one unless you're given the temperature, or you know the temperature, or you assume the temperature. And also, there's no pressure in here. So if you see in the problem and they're given a pressure, it's probably going to be the top equation, not the other one. And then at constant volume, we have delta U is equal to the number of moles times CV times delta T. But enthalpy, if we're at constant pressure, then we use CP, delta T, times the number of moles. That's the heat of reaction or the heat of the process exchange. And then that's delta H. So we can sort of summarize that as delta H is NCP delta T. Delta U is NCV delta T. So we see those kind of equations look very similar to each other. The only difference is the heat capacity at constant pressure or constant volume. Now, if we rearrange those, notice that the heat capacity is delta H over delta T. It's the partial derivative of enthalpy with respect to temperature at constant pressure. This constant pressure here. And the same with U. If I move delta T over on the left, we've got the derivative of U with respect to temperature at constant volume. So that's CV, constant volume. And this is the relationship that I want you guys to commit to memory. I put little stars on it, okay. And that is that CV plus R is CP. So we got really good at calculating CVs, right? With the 3/2 R for translation, 3/2 R for rotation if it's nonlinear. If it's an active vibration, you get a unit of R. And so that's CV. And if you want to go to CP, you just add one more unit of R. Okay. So that's it right there. So we're good at this. We know this. What do I say? Yay. Okay. Yeah, I got that. And then we put an R on there and we get CP. Very important equation, especially because when we get into expansion engines, heat engines, we're constantly calculating the ratio of CP to CV. So you got to calculate CV for your working gas, and then you add an R, you got CP, and then you do the ratio and you get gamma. So this is an important skill to be able to calculate CVs and CPs from the molecular identity of a gas. Like if it's a diatomic, it's linear. You know, if it's water and it's bent, you know, it's nonlinear, and that changes CV. Okay, so now let's get into the second law of thermodynamics. So this is where your notes kick in again. We calculated this area under the curve, and that was the work. And this was an isothermal expansion. You see the pressure changes as nRT over V. So the pressure drops as we expand the volume at a given temperature. And we calculated this extra little area of work up here. So we have the work for this system. And then this second law of thermodynamics says it's not possible to take in heat and do work 100%. But that's what we're doing for this one leg. And so it seems to contradict the second law of thermodynamics, right? This is the equation for the work done. We have VF minus VI, or over VI. Take the natural log, multiply by the temperature, gas constant, number of moles. Change the sign to indicate that work is going out of the system if we're expanding. And then we can also calculate with the first law here that it's a delta U is equal to Q plus W, and work is neither created, or energy is neither created nor destroyed. And so what we see with this process is that work is equal to minus heat. And so heat goes into the system, work comes out of the system. That seems to violate the second law of thermodynamics. But if you'll notice, the second law of thermodynamics has this important word right here. No cyclic process is possible. Okay, so that's in creating a thermodynamic cycle. This is just one leg. So yeah, this leg can convert heat directly into work. Okay, but a cyclic process would have some other legs here, like maybe an adiabatic leg here, where there's no heat exchange, only work is done. And then we might have, since this is a colder temperature now, if no heat flows in and we expand it, the temperature drops. And so now we're at a colder temperature. And then if we do an isothermal compression and push it back uphill a little bit, okay, so we reset the system by putting work into it, and then we bump it up with an adiabat here, then we've got a cyclic process. Okay, so the area under this curve here on the way back up is work we've put into the system, but it's at a cooler temperature, so it's easier. So we put in less work into the system to reset it, and then when it goes to the top right and down, we get more work out. So we put a little work in, we get more work out. And that work in, okay, some of the energy is lost to heat, and so we don't have a complete conversion of heat in to work out. We're losing some of that heat, and so that's the second law of thermodynamics. And it's because of entropy that we can't do that. We can't have a perfect conversion of heat into work in a cyclic process. This also is what drives spontaneity. So this, again, we've seen this, balls bouncing. I have a few here. I bought these. I saw these one time. I don't remember where I saw them, but they made me laugh so hard. Y'all may have to, let me do this over here on this table. Okay, I'm gonna make a prediction. Okay, so you've seen balls bounce, right? This is your normal ball, right? Why does it not bounce up as high as it does? I'm holding it here and I'm dropping it. Why doesn't it come back up to here? Where though? Sound and heat. Yeah, we hear some sound coming out, but also heat. So if I kept doing this over and over again, the ball would heat up. Right now it's not very much. I'm only giving it very little energy, but we can see it very easily. But it's not a lot of energy, so it's not heating up. Also the table. It hits the table and that energy is lost, and it's not enough to restore the energy back to the ball. This one is a different polymer. I thought this one feels harder, but it shouldn't be. But anyway, this one has a polymer structure in it that loses more energy when it hits. Okay, watch this. Isn't that funny? This one is a very inefficient structure and is able to absorb more energy. and not hold it in a manner where it can bounce back up. So that in engineering materials, this has a higher loss modulus. It doesn't, when you give it energy, it doesn't store it in a way that it can be given back. Whereas this one does, this polymer. And it has to do with the cross-linking of those polymers and their structure. Okay. That over years, they've also got a different sheen. You can see them. I'll just pass them around. Like the one that is like a dead cat bounce, it's not as shiny anymore. When I first bought them, they were both kind of the same luster. But it's kind of interesting. So the one hits and it loses that energy to sound and heat, disordered motion. And so entropy, that's sort of the tax we pay. Is we have this disorder tax. Whenever a process is going along, we never, we get taxed. Some of that energy is lost to heat and sound. You can drop them by yourself. Yeah. Okay. You didn't want to play it? Isn't that funny? That just cracks me up. This one is what cracks me up because it falls and doesn't bounce, And you normally see something bounce, but this is just crazy. Okay. I'm easily amused. Absolutely. I used to do this too. When I would get bored, I would pull my pen cap off and just barely put it on like that and drop it. Barely put it on just to see that. That just makes me laugh. There's no bounce. It falls over. Anyway. But there, I'm storing the energy in the friction of that cap being put on. It falls down and the energy is stored in the friction and it doesn't bounce. And anyway, so keeping track of the energy is what we're doing in this course. A lot of times I think of this part of the course, thermodynamics, as accounting for chemists. Like we're keeping track of where the joules went. So. Okay, now the reverse reaction is not impossible. It's just improbable. So, all the things that we set down on the table, it's not impossible that they would just jump up in the air. The table is vibrating like crazy. And what it would require is that all of these random motions in the table would all of a sudden, hit the bottom of the object and cause it to bounce up. Again, it's not impossible, but what would happen is, remember we talked about the weighting factors of all possible states in a substance. That's what Boltzmann was doing to calculate the entropy. And some standing wave in the table that would be enough to bounce your earbuds up off the table or this ball off the table, that's a possibility, but compared to all the other possibilities in that table, it's extremely rare. And so it just wouldn't happen. Y'all familiar with this movie here where she says, if there were 1 million guys on this planet, you'd be the last one that I would go out with. Okay? And instead of being distraught, he gets excited. He says, so you're telling me there's a chance? Right? No, she's telling you there's no chance. But he's holding on to that one possibility out of 1 million, and that's kind of what we're talking about here. It's not impossible, but it's improbable. Okay.
How do you feel about spontaneous combustion?
Yeah, it's improbable, okay, but not impossible. Because we live in an oxidizing atmosphere. We're surrounded by the oxidant, and we're pretty good fuel. All the fat in my body, man, that burned like a candle, Now, I don't know, are you talking about people spontaneously combusting or?
Yeah, I feel like that's usually what I see when it's talked about.
Yeah, we were in Oregon, and there was a reservoir that, I don't know why, maybe the dam just failed. It was a natural reservoir, and it was empty. And we went up there to fish. It was on the map, and we drove up there to fish, and it was empty. So we're like, well, no fishing here, right? But they had signs everywhere, and it said, do not enter unseen voids and spontaneous combustion fires and so on in this area. And so there, the mud and muck and organic matter was sort of overgrown with like surface grasses and stuff like that, and it would generate enough heat that it could catch fire. And so some of that biological activity would generate enough heat, and it was so insulated that it would get up hot enough and then some of the grasses and things would catch fire. So at least that's what the sign was warning us about. We didn't see any spontaneous combustion fires, but. And so let's talk about entropy. The entropy of an isolated system increases in the course of a spontaneous change. So the simplest isolated system is the universe. So the nature as a whole is moving towards disorder. I would say just, populating more energy levels. This also tells us that things that are solid are going to want to go towards liquid or straight to gas, like sublimation. Our planet is both losing mass and gaining mass. It's gaining mass from the sun. We're getting blasted with particles all the time. Electrons, protons are the most common, but also whole nuclei of ejected material are coming in and hitting our atmosphere. But we're also losing a lot of mass. Just ions that reach escape velocity and are able to leave the planet. So. That's entropy, because you get a particle out in a large volume and its translational energy levels are so many that they have a huge entropy. So that's kind of how we know our universe is fairly young. 13.7 billion years doesn't sound like young, but we still have a lot of low entropy structures in our universe. We have planets like ours with water. Again, that's pretty low entropy compared to a gas, which has a high entropy. So when they talk about thermodynamic heat death in the expanding universe, that would be when all of the planets have sublimed, all of the liquids are gases, all the solids are now gases, and we just have atoms spread around the universe. Yeah. So that's a long way away, probably. We have lots of large structures in our universe, and it doesn't seem like something we should worry about at this day and age. But as a kid, I was freaked out about that. I was like, our sun's going to explode and boil a planet? Yeah, eventually, but it's not something it's going to happen next week, so you don't have to worry about that. And so then for the reversible isothermal expansion of an ideal gas, we have this, again, this single leg can be heat and work, equal and opposite signs. And then we have the entropy description, where we take the derivative of the heat over temperature. And so this is, again, that reversible isothermal expansion of an ideal gas is nRT ln VF over VI. Well, we divide it by T, and we get the entropy here. So this is our entropy equation for the reversible isothermal expansion of an ideal gas. Okay, so then let's look at the third law of thermodynamics. And honestly, this right here is all you need really to think about in terms of the third law of thermodynamics. What happens? You guys just did a whole test on this. When the temperature goes to 0, what happens to Q? It goes to 1, right? And entropy is K ln Q. And when temperature goes to 0, Q goes to 1. And natural log goes to 0, and therefore entropy goes to 0. So we already know the third law of thermodynamics. What happens to entropy as temperature goes to 0? Q goes to 1, and entropy goes to 0. But anyway, at T equals 0, all the excited state energy has been sucked out of the substance, and the partition function is reduced to 1. So if S is a measure of disorder, then that disorder goes to 0 as T goes to 0. That's the Nernst heat theorem. And so this is the third law typically stated like this: the entropy of a perfect crystalline atomic substance is 0 at T equals 0. The reason they get into the perfect crystalline atomic substances, there can't be any other kinds of disorder, like different crystal structures that might have different partition functions. There can't be, two different types of atoms. Again, the way you put those together, is it A, B, B, A, or A, B, A, B? All those different kinds of things are entropy. There's different ways to construct the system. So a perfect crystalline atomic substance, there's only one way to make that system. Therefore, it has a very simple partition function, and therefore it would go to 0 as temperature goes to 0. So then the other thing is the practical result is we have a reference point, so we can make tables, and that's good. We'll do the Kahoot in a minute. So we'll get to the tables in a second too. So consider a system and its surroundings at the normal 1 atmosphere transition temperature. So at 373 Kelvin, that's the boiling point of water. Okay, we have evaporation and condensation of steam. Okay. And then we also have the melting and freezing of water, equilibrium with ice at 273 Kelvin. And so this is at equilibrium. So delta G of melting is 0. Then delta G is delta H minus T delta S. And so we can set that equal to 0, and we can solve for delta S, and it's just the enthalpy of melting, which we can measure, divided by that temperature of melting. And so that's the entropy change for that particular transition. So this is our equation here. Entropy is delta H over delta T. No, not delta T, delta H over T, because this is for transitions, phase changes. And so this freezing and condensation are exothermic. Okay, and so they show a decrease in entropy. If we're cooling things down, if we're freezing, we're taking the liquid and making a solid, and so that's a decrease in entropy. If we're taking a gas which has a huge entropy and we're consolidating it into a liquid, that's a decrease in entropy. Melting and vaporization are the other opposite direction. So since delta H is positive, then we have an increase in entropy.
How come delta G is 0?
For equilibrium, so remember, delta G is for spontaneity, but when we're at equilibrium, we're at the minimum of that delta G well. So if we have a reaction, I'm just reviewing for you. I saw you guys nod your head, but we'll take this. So this is all reactants. This is all products, and we're going to plot we're going to plot G up here. Okay. And we might have Gibbs energy for the reactants there, Gibbs energy for the products there. Notice it's negative going from reactants to products, and so it's a spontaneous reaction in the forward direction. But it really looks like this. It dips. Okay? And so right here, that's the minimum. This is the equilibrium point. So because that delta G dips, then there's a point right there where it's 0. Okay, delta G equals 0. Notice if we have all products, it'll run backwards. Okay, because it would be spontaneous going in the reverse direction to make a negative delta G. If we have all reactants, it's negative in the forward direction, but somewhere in the middle it goes through 0 because there's a dip. And so that's where we would be for melting and freezing and vaporization and so on. At those phase changes, the liquid and the solid at melting are in equilibrium with each other, so they have a 0 delta G. Okay. Let's look at entropy variation with temperature. So these are some really interesting plots. So we have that. The calculation of entropy, we can start out with this initial entropy of value, which takes into account essentially at temperature 0. If it's not a perfect crystalline solid, okay, then it might have a non-zero entropy at 0 Kelvin. So we start out with the initial entropy at initial temperature, and then we can integrate that heat going into the system and calculate the entropy as we go up in temperature. So if there's constant P and PV work only, so we're using a constant pressure situation, we have the heat capacity at constant pressure, and is substituted in for Q, okay, and delta T there. And so if Cp is assumed to be constant over the temperature range of interest, then we have this long integral where, again, we have the entropy, that sort of 0 point entropy there, and then going from 0, if the if the final temperature, if it's still a solid, then we would just integrate that from 0 to the final temperature, or temperature of fusion is what this is. So this right here is TF, temperature of fusion. It's the melting point. So if it's still a solid, we would just go up to whatever temperature we're at. Let's say if we're integrating to here, then we would have this entropy piece right here. Okay. But if we go past the melting point, then we take into account the melting piece. So this is melting. And then if we're heating up the liquid, we would stop. Let's say if our temperature was right here, then we would stop at this point. But if we go past the boiling point, so this is heating up the liquid, and then we have the boiling. And then we're just heating up the gas. And so basically this is pointing out that we have the equation for entropy, and we can integrate all of this up. And we can use this to calculate the entries in tables for 298. And so that's what we have in our system is thermodynamic tables with all of the entropy values at 298 and 1 atmosphere pressure. Let's look at some data for oxygen. So here's again, this is the heat capacities. Let's look at the heat capacities for a little bit. So look at how they grow in terms of the solids. So there's 3 solid forms of oxygen. Now that seems strange. We cool oxygen down, it turns to a liquid, keep cooling it, it turns to a solid. And then we have solid 1, solid 2, solid 3. That's weird. We haven't really talked about multiple solid phases. Y'all haven't had inorganic yet, have you? No. Did y'all cover in your freshman course? Because freshman course and inorganic are kind of related. Freshman chemistry is a lot of inorganic in it. Did y'all talk about crystal structures? A little bit? You had face-centered cubic, body-centered cubic. Remember those? Okay. Well, there's different ways to put atoms in a box, right? And think about what you did with your oxygen dimer calculation. We had the T-shape, we had the linear, linear like this, we had the square, we had the rhombic. All of those are going to be different solid types. So let's say we had a solid oxygen where they were square, okay? And then we cooled it down further, and maybe a colder temperature version would be the rhombus. And so all of the oxygen molecules in that solid went through a phase transition where they all tipped over and made rhombic structures. And then what if we cooled it down even further and it said, I really want to get to the lowest energy structure, and they go to the tetrahedron, which was the lowest one. So those are different structures. So this is where that lab kind of plays in or comes in. We have oxygen with 3 different solid structures. Now we're going to get into phase diagrams in the next part of the course. Well, yeah, I think it's next. It's after the heat engines. Okay, but that's what we mean by solid 1, solid 2, solid 3. Now the different solids have different heat capacities. Just like we have the 3/2 R and 5/2 R and all of those things, the solids are going to have a different acoustic vibrational structure, and they're going to have different heat capacities. And this solid here, solid 1, has a solid CP heat capacity. And then solid 2, its heat capacity is actually a linear function of temperature, it looks like. And the same for solid 3. And then down here we get into sort of the quantum effects, where the heat capacity goes to 0. But we have, a range where solid 3, solid 2 are both, CP is a function of temperature. So and so in this here it says CP solid delta T over T, or we're integrating with respect to temperature. But this could be temperature dependent, and we would just have to have the equation for that heat capacity for those regions. Now let's look at the liquid. Notice that when we go to the liquid, we have a big jump in heat capacity, which again reflects the higher partition function for the liquid because it's got more flexibility in the molecules moving past each other. You could think of it kind of like the molecules now have a bigger box because now they can move around each other. And we know from a particle in a box, if you expand the box, the energy levels crush down. When they crush down, the probability of populating all those energy levels goes up, and that's entropy. So the liquid, because the molecules are mobile, has a higher entropy. Now, what happens when we go to gas? It really drops. And it drops because we lose a lot of those other things that can happen in the liquid, right? These sort of sliding past each other and all of that. Those are active vibrations in the liquid that disappear when we go to the gas. And in oxygen, it's just a diatomic molecule. So when we go to the gas, we have translation, rotation, and vibration, and that's it. We don't have any other possibilities in terms of what a gas can do. But in a liquid, they can move past each other. They have a lot of active vibrations, even though it's still O2, but we're talking about whole molecules vibrating past each other. And so we have a lot of units of R added in the liquid that we don't have in the gas. And so this, what would be the heat capacity for O2? So let's do CV for O2 at room temperature. See, here we're at 100 Kelvin. So this, we're way over here at 298 Kelvin. What would be the CV for O2? You guys did this last time for the test. You want to add it up by motion? So we have translation. What do we have? 3 halves R. Okay, and then what can oxygen do in terms of rotation? Yep, 2 halves R, right? Because it's linear. And then vibration at room temperature, what's this? I don't remember the O2's vibration, but what is a carbonyl, like in the infrared? Carbonyl stretch. That's a carbon double bond to oxygen, 1600. You got it, 1600. That's one of your IR frequencies you should just kind of have in your noggin. 1600 for carbonyl, because that's where your aldehydes, ketones, acids, any of those C double bond O's. So oxygen is going to be somewhere near there. It's nowhere near 200 wave numbers, and room temperature is 200 wave numbers. So is the O2 vibration active at room temperature? No, it's not. So we don't add an R for that. So we add all this up. CV is equal to 5 halves R. So why is this 7 halves R? Well, it's 7 halves R because this is CP. So CP is equal to CV plus R. So we get 7 halves R. So oxygen from 100 Kelvin on up has got the theoretical equipartition heat capacity. So we could come up with this very number here. So that's good. So this one is CV, and this one is CP. So that's pretty cool. Now over here, if we were to integrate all those CPs and CVs and so on, this is the entropy of those. So we can see the entropy of the solids are pretty low. Every time you go through a transition, you get the entropy of that transition, which is the delta H of that transition divided by the temperature of that transition. So we have these big jumps. And look at the biggest one when we go from liquid to solid, liquid to gas. We have this huge jump in entropy. And then we have the entropy of the gas. And then let's look at those tables. We can calculate the enthalpy or entropy of a reaction using the tables. So let's use the example of water and oxygen hydrogen and oxygen making water. So we look up the standard entropy for each reactant and product, and pure elements must be included. We'll contrast that with Gibbs energy and enthalpy later. So here's the table. You'll get this exact table on your test. So we look at here, we've got water. Now, one of the things we got to make sure is which one are we dealing with? We're dealing with water gas or water liquid. So you look back at the reaction, we're dealing with water liquid, because that's going to be a big error. Numerically, you're going to screw something up big time if you don't pay attention to the phase of the reactants and products and so on. So it's 69.9 minus 205 for oxygen and 130 for hydrogen. But we got to take into account the number of moles too. So this is what we have. We have 1 mole of hydrogen, 1 mole of water, but a half a mole of oxygen. So you got to pay attention to that. So it's 1/2 times the 205 joules per Kelvin. And then again, because we're multiplying by these moles, right? We have 1 mole times 69.9 joules per mole Kelvin, but the moles cancel. And this is 1 mole, 130 joules per mole Kelvin, but the moles cancel. Half a mole of oxygen. So the units of this are joules per Kelvin. So this is for that reaction as written, minus 163 joules per Kelvin. And then you can look at the reaction and we can say that that's joules per mole Kelvin for hydrogen or joules per mole Kelvin for water. But we can't say joules per mole Kelvin for oxygen because we only have half a mole of oxygen. So we would need to multiply that. Again, that's for that reaction, and that's for half a mole of oxygen. So how much per mole of oxygen? That's for half a mole, so it would be double that for a whole mole of oxygen. So what have we done? Well, we looked at the third law of thermodynamics. Again, the second law is no cyclic process can perfectly convert heat to work. Okay. It looks like the isothermal expansion and compression violate that, but they're not cycles. They're legs of a cycle. And then secondly, we looked at the third law, which sets the entropy of a perfect atomic substance at 0 Kelvin. That allows us to make tables. We can integrate anywhere along the temperature axis and calculate Cp and Cv and the entropy. And then once we have the tables, we can use these up in like a thermochemistry way where we can take products minus reactants and calculate our entropies. So we're just going to keep applying this. We're going to get into Gibbs energy and enthalpy and apply it to motors. So you guys are going to know a lot about heat engines.